Here is a more formal definition of additive wide Gaussian noise channel. Okay, so here Yi is the receiver symbol for ith channel use. Xi is the ith symbol sent at the ith channel use, and Zi is the noise. And the symbol you transmit and the noise that is added at the receiver are assumed to be independent. That's reasonable, right? They should have no correlation at all, right? So Zi is Gaussian distributed with a mean zero, variance n, capital N. So in this particular node, I will use N to be the power of the additive noise, symbol power. Okay, symbol energy. So I'm using power and energy interchangeably in this node. It is just, you can just say that it is a expected value of the expected value of the random variable Zi, and whether you divide it with the time unit. In the case you divide it with the time unit, then it becomes power, and if you don't divide it by the time, then it becomes the energy. Okay, so it doesn't matter. So this is you just need to say remember that N is the second moment of Zi, random variable Zi. So here constraint is put on the input Xi. So you have to use only search only so much power at the transmitter. So expected value of Xi square should be limited to P. Okay, so use of the channel is basically you use this channel n times, and when you do that, the sample power of your code word is less than or equal to P, but there is no way, there is no reason that you would use a smaller power than P. Okay, so that's the maximum power that is allowed, that is allowed. So you should use maximum power. Okay, and successive use of the channel trying to exploit the law of large numbers. So that's the Gaussian noise channel. And I will refer to this as equation number 1. So here Xi is any random variable. So it could be uniform distributed, or it could be binary distributed, with the alphabet +1 and -1. So Xi, what's only determined is the power, okay, P. And in this channel, the Zi, the distribution is determined, okay, to be Gaussian, and power is also determined. That should be N. So here we have two things, parameters defined, which are P, which is signal power, N, which is noise power. So this we call signal to noise ratio, right? Signal to noise ratio. And if we define signal to noise ratio in decibel, that should be 10 times log 10 P over N. Okay, so when we say SNR, it should be this ratio. When you say SNR in dB, it should be this. So in, let's say, SNR dB is negative 10 dB. What does that mean in terms of SNR? SNR, that is, SNR should be 1/10. So noise power is 10 times larger than the symbol power in this case. If it is negative 20 dB, SNR is 1/100. Negative 30, 1/1000. If it was positive 10 dB, SNR is 10. 20 dB, 100. 30 dB, 1000 SNR is. Okay, so that's the setup for the Gaussian noise channel. Okay, and let's move on. And the binary signaling over AWG. And in this case, we again fix the signal power to be P. So expected value of X is P. And then we choose this A to be that. And then X could be plus A with a probability half, minus A with a probability half. Then you can satisfy this power requirement. And then Z is additive noise, Gaussian noise, additive Gaussian noise. And we can assume maximum likelihood detection. So, and then we can analyze the probability of bit error. Bit error is half times probability of Y less than 0, given X is plus A, and probability Y is greater than or equal to 0, given X is equal to minus A. But since each probability here is the same, so we just need to consider one of them, and then maybe we can consider this one, and then this one is a Gaussian distribution, so we just need to know. So we can draw a picture. Basically, this probability can be described as okay. So that's the normal Gaussian distribution with mean 0 and variance of m, right? And the error probability is this one or this one maybe. Okay, so let's get rid of this. I think this one was right. Okay, so let's erase this part. Oops. This part, okay, that's this one. And we can describe this way with the PDF. So negative infinity to A is this probability. So if you take that away from 1, that's this probability. Okay, so we can describe it as a Q function, and then Q function is well defined. Basically, if you use Google search, then you can find the Q function, and then here we have this Q function. Basically, if you have an argument here, then you can exactly determine what the Q function's output is. Okay, so you can use that, or you can use MATLAB or Python to program this, and then you will be able to evaluate the error rate. But the problem here is again that if you use a symbol all alone, right, repeatedly, then you cannot get rid of this probability. Probability of error will remain very large. But if you give some relation between the transmitted symbols, right? Give some kind of relation, as you have seen in Hamming code, then basically you can get rid of this probability of error. The problem of sustaining probability of error. So we can make the probability of error goes down to 0 as we increase n. So that's the message. Okay. All right. I will stop here momentarily, and we'll talk about channel capacity.